we were looking at the way a chemist looks at the world. Basically, a chemist will want to define matter, and matter, of course, is anything that has mass. And we looked at the fact that we can divide matter into two main categories: mixtures and pure substances. And in this chapter, we are particularly interested in air. And so we defined air as a mixture, and mixtures need to be defined by their components and the concentrations of the components in the mixture. So we looked at the major components of air are nitrogen and oxygen, and then we started looking at some of the minor components. And we recognized that to understand, the mixture, you have to know what the components are, and the components are pure substances, either elements or compounds. And elements and compounds are defined by their name. Their name tells you what is in that particular pure substance. For example, carbon dioxide is a pure substance made of carbon, one carbon atom, and two oxygen atoms per molecule of carbon dioxide. So that's what we talked about before. Today we're going to take start taking a look at, where do these pollutants come from, the minor components of air. And so what you'll find is, we're going to turn now to the document camera. Is here on Earth. It's the way the Earth has evolved. But the pollutants, they have varying concentrations depending on where you are, and they mostly come from human activity. Largely, the pollutants we're going to look at come from the combustion of fossil fuels. And so we combust fossil fuels in order to extract the stored chemical energy for modern life. So we're going to take a closer look at that today. All right, so first of all, you may ask yourself, let me tell you something. I need to tell you something before we move on. This is really important. Before you start viewing or continue viewing this particular lecture, I'd like to make sure that your teacher has already given you this POGIL exercise called Balancing Chemical Equations. You should complete this POGIL exercise before you view this video. If you have not done it, just stop the video, do the exercise, and then you can return to the video. Okay? Alrighty. So combustion. We said that most of the pollutants are a result of combustion. So we probably ought to understand, what is combustion. Combustion is defined as the rapid combination of oxygen, that's an element, with some other substance, either an element or a compound. So combustion is actually a type of chemical reaction in which one of the reactants is oxygen. All right? And combustion equations are chemical reactions that are represented using chemical symbols, and they obey the law of conservation of matter. All right? So combustion is just a type of chemical reaction. I have another worksheet for you all to do after you finish the POGIL worksheet called Classification of Chemical Reactions. This is just a practice identifying types of reactions. I don't want you to think that a combustion reaction is the only type of chemical reaction. Actually, there's many different types, and you can identify the types by looking at the reactants and the products. Remember, the reactants are on the left-hand side of the arrow, and the products are on the right-hand side of the arrow, and you're looking for a change. The total number and type of atom of element is going to be the same across the reaction. There's just going to be a rearrangement. And in the case of the combustion reactions, we are combining some element or compound with oxygen to form a new substance. And the different types of reactions other than combustion are combination reactions, decomposition reactions, single replacement, double replacement. And you can figure out which types those are just by observing those reactions on that worksheet that I gave you. But I'll tell you that a combustion is a special type of synthesis reaction, okay? So a combustion reaction is a special type of synthesis reaction. And a synthesis reaction, or sometimes also called a combination reaction, is a reaction when one or more elements or compounds combine to form a new compound. All right, and so in the case of the combustion, it's a special type of synthesis reaction in which oxygen is always a reactant. All right, So you can identify a reaction as a synthesis reaction, and further you can identify it as a combustion reaction if oxygen is a reactant. Okay, so let's look at an example of a combustion equation. Okay. In this particular combustion equation, we have carbon, elemental carbon, combining with oxygen to give or yield carbon dioxide. So you can see it's a combination or synthesis reaction, a special type called a combustion reaction, because the element or compound, in this case it's an element, is combining with oxygen to give us a new compound. Okay, so that's a combustion equation. Sometimes we call it burning carbon. Okay, when you burn something, oxygen is the reactant. That's combustion is a fancier word for burning. Okay, so carbon burns an oxygen to give carbon dioxide. All right, now you'll notice that this particular equation here is a model to describe what we see. If you take a pure sample of elemental carbon and combine it with oxygen, you're going to get just this one product, carbon dioxide. This is another way to model the same chemical change. In this way, we call this a space-filling model, where we have this one single sphere is representing the elemental carbon. These two spheres that are pushed together here in a covalent attraction is an diatomic element, two atoms combined as a molecule to give you the way oxygen exists in nature. And then this is the space-filling model of the carbon and the two oxygens chemically combined to give the molecule carbon dioxide. And you'll remember from the last lecture in your homework that this is a molecule. It's a covalent compound because it's a combination of non-metals. That's going to give us this special case where we call it a molecule. A covalent compound is another word for a molecule. All right, so we have different ways to model the combustion equation, and you should be familiar with both of these ways that we model it. Okay. Here's another example of a combustion equation. In this case, sulfur is the molecule that is combining with oxygen to give the compound sulfur dioxide. It's a molecule, sulfur dioxide. And again, you can see we can model it with letters and little numbers, or we can model it with these spheres that we call a space-filling model. They both tell us the same story. And as a chemist, when I look at this S, I think single atom of sulfur. When I look at this O2, I'm actually thinking two oxygen atoms chemically combined. And when I see this SO2, I'm actually thinking sulfur with two oxygens attached. Now, you may not be able to, at this point in your career, look at SO2 and know that the S is in the middle and the two oxygens are what we call terminal. We'll get to that in the next chapter. For now, I just want you to know that in a molecule of sulfur dioxide, you can read the name properly, sulfur dioxide. If I said sulfur dioxide, you could write SO2 and you could model it this way or some way. It doesn't have to be exactly right at this point in the game, as long as you get one sphere for sulfur and two spheres for oxygen. Okay, so you can see it's balanced. Matter is conserved across the chain.